Okay, so a few classes back, we started the evaporation, right? And evaporation is like the water actually evaporated because of the heat from water surface or from the plants and everything. And we said that there are what? Four widely used methods we will use for calculating the evaporation, right? And we did that. The very first one was the simplest one, evaporation by using the fan. And then we use a little bit complex one, which is the evaporation by the aerodynamic method, which simply says that the evaporation will be dependent on the differential vapor pressure between the water surface and the air at a specific level, right? Then on Wednesday, we discussed two measurement methods. The one was the energy balance method, one was the combination method by Kenyon. Now, from the name of energy balance method, we kind of know what we are dealing with. We are actually considering a control volume for which watershed or for which area we want to calculate evaporation. And we are trying to find out, okay, what is the incoming energy, or what is the outgoing, or what are the outgoing energies are on that control volume. And when we discussed in details, we found out that, okay, obviously we know for evaporation, solar radiation is the one, which is the source of energy. But if you look at all the like name, it says that net radiation. That's only because the amount of solar radiation coming to the earth, obviously not 100% of them are staying at earth. Some of them are actually getting reflected, right? So that's why it's called the net radiation, and that is the main inflow or influx of energy. And for the outflow, obviously the very first one is energy required to do the evaporation for a unit mass of water. The second one is to warm the air in between water and air layer. That is a sensible heat flux H. Another one is the heat flux, which is in between different soil layer or different water layer, right? So that's what we discussed. We also discussed there are few minor energy source here or working on this control volume, like the photosynthesis, respiration, or horizontal movement of air, something like that. But those are insignificant. So unless we have very detailed information, we will not consider those in our calculation, right? So that's where we stopped. And oh no, we actually discussed the Penman method also. So Penman method is the weighted average method we discussed a little bit. Whenever we have a weighted average method, that means we will have two components and we need to assign some weight factor, right? So that's what we did in the Penman method. Since it's a combination method, they use the energy balance method and the aerodynamic method, right? So we discussed all the details, but we didn't get time to do the mathematical portion. So that is the plan for today. We will do the energy balance method and combination method by Penman, class example 16 and 17. And if we get time after that, we'll discuss a little bit about the evapotranspiration. Okay. And just to remind you, your homework 3 is due on Monday midnight. So you will have a chance to ask me question on Monday class. So please come up with question if you have any. Okay. So let's start working on class example 16. Now for 16, if you can remember about the energy balance method, we had two big equations and we need to do back and forth with different tables. So just bear with me. It's not difficult. It just you need to go back and forth in tables multiple times. Okay. Okay. So who will read the class example 16?
On the daily evaporation from the lake for a day out of the following data were.
So air temperature at 4 meter is 30. Relative humidity, we know the wind speed. Then what we need to do? What do we need to do? Compute?
Oh, compute evaporation by energy balance method given daily flow ratios
beta equals to 0.1, yeah.
And the,
N over N,
no, N over N equal to 0.7, and the
extraterrestrial,
extraterrestrial radiation at location is equal to 40 million squared disregard the solar.
okay, thank you. You may notice one word I said that copied from class example 14. So this is the same class statement we did for class example 14. So this time we will solve the same question but using a different method, and we will compare the result if we can get similar result or not. Okay. Okay. Now there are a few things which is kind of new to you, which is the daily Bowen ratio, which is very much related to like warm up air, that part. N over N is the total sunshine hour over like the measured sunshine hour over available sunshine hour, something like that. And extraterrestrial radiation, which is actually the RA, or like the total amount of radiation which is coming from the sun to Earth. Now the RA is given 40 megajoule per meter square. For any reason, if this RA is not given, we need to actually use the table 3.3. Are you seeing that total daily solar radiation received on a horizontal surface at the top of the atmosphere? That is actually the RA. Now for the Virginia, it's in northern hemisphere obviously, and the latitude is kind of 40, it's not exactly 40, maybe 39 point something. So for any reason, if it's not given, we need to find out from this table what will be the RA. Okay. Okay, so let's start working on that. So we understood the question, like what they are asking us to do, right? So they are asking you to do calculate evaporation using the energy balance method. So what we will do, we will identify all the given values, and then we will try to find out, okay, which value is the unknown one, right? Okay, let's start working on that. All the given values. The very first one is RA, which is 40 megajoule per meter square. Okay. What else? Air temperature is 30 degrees Celsius, and the relative humidity is 25%, and the wind speed 6 meter per second. Beta is 0.1, N over N is 0.7. And they said that this we get the soil heat flux, right? So which is Z equals, actually G equals to 0. Right? We need to find out ER. ER is the evaporation by the aerodynamic method. And then what we will do, the equation for ER is Rn minus G . This one, right? Okay. So we need to find out what parameter we already know and which parameter we need to find out. So Rn is obviously related to the Ra, but we need to find out that. Before doing that, let's find out if we can cancel any term or something. So what is the value for G? 0. Density of water. You can check the density of water at the air temperature, but density of water is actually the incompressible fluid. So the temperature will not affect that much unless there is a huge difference. Now 30 degrees centigrade, it's kind of like our regular, little bit higher than our regular temperature here. So you can check the table or you can directly use 1000 kg per meter cube. Okay, so that's what I will do, 1000 kg per meter cube. And I know the Bowen ratio, which is 0.1. Now I don't know Rn, I don't know the lambda, right? Now the lambda was actually the latent heat of vaporization. We need to find out lambda from table 3.2. Okay, so let's find out. All of you have your table 3.2, 3.3. That's with your previous class lecture. So let's go to that. This one. This is the temperature 330. Okay. Now for 30, that is the lambda, latent heat of vaporization. What is the unit for this lambda? Can you tell me from, maybe your copy has better view, because megajoule per kg, right? That simply tells you to evaporate 1 kg of water at this temperature, the energy required is 2.43 megajoule. That's why it's megajoule per kg. Okay. So 2.43, I will write down that 2.43 megajoule per kg from table 3.2, right? Okay. So now the only thing we don't know is what? Rn. So that's what we need to find out. What will be the Rn? So what I will do, I will go to the next page to do the Rn because I will need space. So are you done up to this point, everyone? Okay. So the Rn is the net solar radiation. Now help me how to find out Rn. How can we calculate the net solar radiation? We know the Ra, like the incoming radiation. So we need to find out short and the long. Yes, that's correct. So we know in the incoming radiation, there are two types of radiation, short wave radiation, long wave radiation. And for each type, some of the radiation is getting reflected and some of the radiations are actually staying back on the earth, right? So the total radiation will be net short wave radiation, net long wave radiation. So S is for short, L is for long, right? Okay. So we will calculate this. Okay. Now help me with the equation for the short wave and the long wave radiation. What is the equation for short wave? 1 minus alpha, which is the albedo, and 2.5. Okay. So let's see if we know the values or something. So A is the albedo, like the amount of short wave radiation is getting reflected. Okay. So it will depend on the type of surface. Like for the crop surface or something, they can't absorb all the heat. So alpha will be higher for that type of thing or that type of surface. But for the water surface, it can actually absorb a good amount of water, right? So the alpha for water surface will be smaller than the alpha for the crop or something. Now, do we know any value for water surface? The alpha value for the water surface? 0.08. Okay. So we actually discussed that when we discussed here that alpha is the 0.23 for crops and grass and 0.08 for open water surface. That simply tells you only 8% of incoming radiation is actually getting reflected. 92% of that is getting absorbed by the water surface. Okay, so 0.08. Okay. What is the N over N? 0.7. And what is the RA? Can you tell me what is the unit for that RA? Megajoules per meter square. All the other things are unitless here. So the unit for RA is actually the unit for RNS. Okay, we will calculate that later. Before doing that, let's find out what will be the RNL. Okay. Now, RNL, I told you to make sure that there is a negative sign. Make sure you use that. So that is the negative sign. What is the other part of that equation? Help me with that. Negative 0.1 and okay, then okay, 1/4, okay, and the sigma e to the power 4. Okay, now we know what is N over N. The ED is actually the vapor pressure at air temperature multiplied with relative humidity. We will find out that sigma is the Stefan Boltzmann constant. He'll give me the value for that. And he is the what? Temperature, right? Now one thing, let's work with the Stefan Boltzmann constant first. What is the value for that? And what is the unit for that? K to the power 4 then? Okay. So are you seeing it's the K to the power 4? K is actually the Kelvin, right? So that's why we know the temperature should be in Kelvin also. So what is the air temperature we have? 30. Do we know the conversion factor between degree Celsius and the Kelvin? What is that? 273. Okay. If on the back, can you see the very last line? Okay. So what is the final temperature? 303 Kelvin, right? Yes. Oh, that is, since this is a constant, Stefan Boltzmann constant here. So if it's given, it's given. If not, you can write down that on your equation sheet, or I will add that on your equation sheet, something like that. Okay. Okay.
What is that, read that little
Uh,
one? Something minus those little ones?
oh, that one? Oh, the Stefan Boltzmann constant. Yes.
And that's like a short with it.
This one, that alpha?
Yeah.
Oh, this one, as we discussed here, alpha is the albedo, which is like the amount, the portion of shortwave radiation which is getting reflected back. Okay. So for a surface which can take more heat, the reflection will be less, right? So that's what you can see, 0.23 for crops and grass, but 0.08 for open water surface, because open water can absorb almost most of the heat. Okay, okay. So now we know most of these things. So let's write down all the values here and let's check. So 0.1, 0.9, what is the n over n? 0.7, right? 0.34. Oh, we didn't determine what will be the ED. Alpha is 4.903, 10 to the power negative 9, and the temperature is 303. Make sure you are using 303 to the power 4. Now, the only thing we don't know is the saturated vapor pressure, right? At temperature 30 degrees Celsius. Which table we should use? We can use appendix C, or table 3.2 is like well organized with energy balance method. So we can use table 3.2 also. So everyone, are we good up to this point? Okay. So I will go to table 3.2 for 30 degree. What is the saturated vapor pressure? 4.243. Okay. So 4.243, and what is the relative humidity? So 0.25. Okay, so what is that answer? You already have the answer, right? Do you have the very final answer also? Okay. What is the ED? 1.061 kilopascal, right? Okay. Now your task is, we did everything on the board. You will find out what is the Rn, and once you have the Rn, you will use this equation to find out what will be the final evaporation. Okay? Yeah. So this is the part you will do by yourself. I will check with you after 5 minutes. So you will give me the very final answer. Now, this is the same question statement as class example 14. And for that one, your answer was 6 point something. This is the third day. You should get the similar answer here as well. Okay? To work with that, I will take you to after 5 minutes. And if you have any question, any confusion, please ask me. This is a good time. Short wave radiation, you should get something around 22. And for the long wave radiation, you got something 5.9. For the long wave radiation, yeah. You know, and all that on file and it's still on the stack. Yeah. You can I got it just in the back on that.
I think my converter.
Okay.
So like if my handwriting's not that great.
But do you, like, can you type on it?
Um, we'll see if I'm like maybe a file or maybe.
Oh, but not on, like, you can't take it any file or something.
I can edit the file. Like I could, it's a PDF where it's on the computer, I could like. Yeah, that is, I don't, but
Oh, okay.
I can't type anything on the computer.
I would have this at someone. Yeah. Do it, but it's just too much trouble to.
It gets get used to it for sure. I like this because it feels like it's going a tablet like yourself. Glass.
Practice my one, but my husband has that. That is good, and I use that for if I need to draw something like that. That's very handy, but. That more, something like that.
Yeah.
But this one is just the writing one. Like, basically, that is that. One additional. So you can show the same thing on there. It's kind of good.
So what you write on there, you can actually see. on
Yeah,
there.
yeah. Yeah, yeah. So what I do, I see the code and I like here. So
Yeah, that's cool.
it's good, yeah. But the problem is if I have to take that home, I need to, that's everything from here.
Yeah.
I need to keep that at school. And that's why I actually bought the tab. Okay, so what is the answer for shortwave radiation?
0.04.
Is that the very final answer? 6.044? Yeah. Okay. What answer you got? Got something? This one, this should be 60 point something. You have some answer? The calculation. Okay, for RNS, I think you should get 22.08 megajoule per meter square. You get that, all of you? And for the RNL, you should get negative 5.92. Okay, so finally you have 22.08, 5.92. Finally, you have 16.16 megajoule meter square there, right? All of you got that? Those who didn't get that, please check your calculation because the only thing you can make mistake here just to be the calculation. All the values we already found that from table and it's on here. Make sure you are doing the 10 to the power 4, all the multiplication form and everything. So our Rn is 16.16. So if I go back here, it's 16.16, right? So what number you got finally? One plus 0.1. I think you will get 0.006 meter per day, right? Since it's the daily evaporation. Now, 0.006, it's not hard to imagine like what will be the length or something. So what you can do, you can multiply that by 1,000 and you can do that 6.6 millimeter per day. All of you have that one? Something there. Okay. That's the class example. Yes.
Go back to the previous one.
Where we calculate the Rn, that one? This one?
Where the point oh eight, so they put a table or like this?
That is actually here. Here. So this is actually 0.08 it can be different for different surfaces, but since we are only working with water surface or the crop or something, so it will be 0.23 for crops and grass and 0.08 for the open water. Okay. You can, yeah, you can have that. So are we good with class example 16, everyone? The next one is way easier than this one and much shorter. So the combination method by Kahneman, since this is a weighted average method, can anyone read the question very quickly? It's the same, again, same question statement, but this time we need to do the class example by using the combination method of Kahneman. So Kahneman, in 1948, he introduced this concept that why don't we combine aerodynamic method by evaporation, evaporation by aerodynamic method and evaporation by energy balance method. And we know that there will be some weighted factor. So let's write it down. Combination method. So EA, there will be some weighted factor multiplied with aerodynamic method, ER. Okay. So let's write it down. What does that mean? It's the evaporation by aerodynamic method, ER, which is the evaporation by energy balance method. Okay. Now, we didn't use the same example, class example for aerodynamic method. So that's why I just gave you the direct answer for the aerodynamic method. What was that? What is the evaporation for aerodynamic method? 5.9 millimeters per day. And the evaporation by energy balance method, you just did that. What's the answer you got? 6.04 something, right? Millimeter per day from class example 16, right? Now the next thing is what will be the weightage factor? So the weightage factor for these two I did the opposite one. Now the question is what is delta and what is gamma? Can you go back to your class lesson and tell me what is delta and what is gamma? This one is psychrometric constant. Basically, that is the difference between latent heat and specific heat. Okay. And the delta is what? Whenever we use delta, we know that is kind of some differential values, right? So this one is actually the gradient of saturated vapor pressure. And from where we can get all of these values? Any idea? Table 3.2, yes. At which temperature? 30. From table 3.2 at air temperature, right? Okay. Now you have again 3 minutes. Find out delta, find out gamma, and give me the very final answer for each one. Okay, so since it's the same class statement, question statement and class example 14, the answer should be 3 equals to 6 millimeter per. Answer. That's correct. Let me check. I got a little bit different 5.9. Okay. Mostly because for this one I actually okay, class, what number you got? At first, tell me what is the gamma and the delta value from table 3.2. Table 3.2. So that is the delta, right? And that is the gamma, right? I think you have the better view on your copy. I have recommended 2 plots in one slide. So it's 2.4.243.0674. Is that correct? Okay. So I will just write down those here. So I got 243, and for this one 0.0674. Okay. 2.0674 0.243. Oh, that's multiplied with 5.9 plus 243 6.04 or something like that. So what is the final answer you got, all of you? Something around 6. I got 5.98. Some of you may get 6 or something. So I will just write down 6. Then you got the correct number this time. Still not getting the correct answer. Okay. So all of you, please complete that. And since we have few minutes, I will just start the evaporation aspiration, but not too much. And to make you happy, see, color copy. Here. So we will just start. We will not do. If I don't want you to. Right here. I will actually stop the recorder.